Uh, Dear students, have a good day. Myself, Professor R. Thakkar. I am working as a professor at VGC Chandkheda in EC department. I have experience of more than 20 years. Today, we will have a talk on amplifier and ideal op-amp for approximately 50 minutes. The outline of talk is, initially we'll have introduction to amplifier, then we'll have classifications of amplifier, then we'll have amplifier specifications, we'll have some introduction to op-amp, we will also study ideal op-amp properties, and then we'll look at op-amp based amplifier circuits. This is the outline of today's talk. Now, before this, I hope you would have studied two modules, one on circuit components, where you would have studied about resistor, inductor and capacitor. Also, you would have studied Kirchhoff's law. You would have studied about meters and measurements. These are the topics you would have studied in module 1. Now in module 2, you would have studied about circuit analysis techniques, where you would have studied Thevenin's and Norton's theorem. You also would have studied about node and mesh analysis, as well as superposition theorem and Y2 delta transformation. Now, today we'll study about amplifier and ideal op-amp. Amplifier, it is one of the basic building blocks of analog circuits. There are actually two types of circuits. One circuit, it is called as an analog circuit. The second type of circuit, it is called as a digital circuit. Analog circuits, it basically processes analog signals. We'll see that what is the meaning of analog signal in the subsequent slides. The second type of circuit, it is called as a digital circuits. Digital circuits, they basically process digital signals. We'll also see that how the digital signals look like. If you look at analog signal, they are continuous in amplitude. They are continuous with respect to time. For example, that if we measure the temperature in this room at different time point, then this temperature can take n number of values. So at each and every time point, there will be one value of the temperature. And there are infinite values possible for the temperature within a particular range. So this temperature signal, it could be called as an analog signal. Now the second type of signal, that is the digital signal. Digital signals, they are discrete in amplitude and they are not continuous with respect to time. For example, if we represent alphabet in terms of electrical signals, then there are 26 alphabets. Now each alphabet could be represented with one voltage level. So then naturally that it will be discrete in terms of amplitude. Now for example, that I'm speaking my name, say Rajesh, then I'll be speaking, say there are 6 letters, R, A, J, E, S, H. So R will be remaining, I'll be speaking out for a certain time period. So that if I represent R with some voltage level, so that voltage level will remain constant up to that time period. Then I'll be speaking out, say A. So A will be represented with another voltage level. So that voltage level will remain constant for the second time period. Like that, actually, there are 6 alphabets. So each of these 6 alphabets, they are spoken out for a certain time period, and the corresponding voltage level will remain constant for that time period. So that is what called as a digital signal. Digital signal, basically, it's a signal which is discrete in amplitude and it is not continuous with respect to time. We have sample photographs for analog signal as well as the digital signal that we'll see in the next slide. If you look at this slide, in the upper part there is analog signal. It is continuous with respect to time. X-axis, that is the time axis. Y-axis, that is the amplitude axis. You can see that at each and every time point there is some value of the signal. So it takes infinite values within a particular range. Now if you look at the digital signal, this digital signal, it's a special kind of digital signal. It's a binary signal. It takes just two values. Okay, these two values could be called as a 0 and 1. For a certain time period, the value is maybe say 1. For another time period, the value is 0. Like that, actually, basically the signal it switches between the 0 and 1 only. Okay, and it is not, wherever it is constant, actually, there its value is not required to be specified. Okay, so that's why that we can say that it's not continuous with respect to time. Now if you look at the amplifier, we have seen about signals. We have seen about the different types of circuits. Now let us look at the amplifier. Amplifier, actually, it is one of the basic building blocks of analog circuit. As we have seen, analog circuits are the circuits which processes analog signals. And amplifier, it is one of the basic building block of analog circuits. There are various kinds of analog circuits. Amplifier, it is one of the analog circuits. It's basically electronic device which increases the strength of input signal. If you look at the amplifier word, that its meaning itself is the amplification of signal. So amplifier, actually, it amplifies the strength of the input signal. During amplification, it has to maintain the shape of input signal. Otherwise, the amplified signal, it won't be useful, actually. The job of the amplifier, it is just to increase the strength of the signal. But while increasing the strength of the signal, the shape of the signal has to be maintained. Otherwise, the amplified signal cannot be interpreted at the receiver side. Okay, now for the amplification purpose, it requires energy. Now this amplifier circuit, it takes the energy from the power supply for the amplification purpose. So basically, generally, in most of the cases, the power supply will be the DC voltage. The input signal, it could be varying signal, actually. So it is called as an AC signal. Okay, so we can say that amplifier, that for amplification of the input signal, it takes energy from the that DC voltage source, and it adds it to the input signal, and that is how actually it amplifies the signal. Now there is that another type of circuit which is called as the attenuator circuit. Now attenuator circuit, it actually reduces the strength of the signal, or we can say actually it attenuates the strength of the signal. Now if we compare the amplifier and attenuator, then the job of the amplifier, it is exactly opposite to the attenuator. Attenuator, it attenuates the signal, whereas the amplifier, it amplifies the signal. It increases the strength of the signal. So this is the basic information about the amplifier. Now we can have that different types of amplifiers. Amplifiers could be classified based on various parameters. So one parameter, that could be the frequency of the input signal which we want to amplify. So that here actually that two types of amplifiers are shown, are mentioned in the slide. One amplifier, it is called as the audio amplifier. Amplifier, it could be used to amplify the audio signal. Okay, so and we know actually that the frequency range of the audio signal, it is within the range 20 Hz to 20 kilohertz. So if there is an amplifier which can amplify the amplitude of the audio signal, then that amplifier could be characterized as the audio amplifier. Now the second category of the amplifier, it is called as the RF amplifier. So if amplifier is capable to amplify input signals whose frequency is outside 20 Hz to 20 kilohertz, here it is mentioned as 20 kilohertz to 300 gigahertz, then that amplifier, it is called as the RF amplifier. So basically that if we want to classify amplifier on the basis of the frequency of the input signal, then we can have two categories. One is the audio amplifier, which can amplify input signals within a frequency range 20 Hz to 20 kHz. The second category, that is the RF amplifier, which can amplify input signals whose frequency could be in the range 20 kHz to 300 GHz. Now, there is a second parameter on the basis of which the amplifier could be classified. That parameter, it is called as the operating point. Depending upon the operating point, the amplifier could be classified as, say, Class A, Class B, Class AB, and Class C. We'll try to briefly understand. What is the meaning of Class A, what is the meaning of Class B, what is the meaning of Class AB, and what is the meaning of the Class C. Now, with the amplifier, one load line could be drawn on the characteristic of the transistor. Transistor, it is one of the device which is used in the amplifier. So we can draw one load line. It's maybe that you will study more about the load line in the higher semesters, in the third semester or fourth semester. So basically, that in the amplifier, there will be one device which is called as a transistor. The transistor will have its own characteristic. Now, we can actually superimpose load line on the transistor characteristics. Then this operating point, if it is at the center of the load line, then the amplifier circuit would be operating for the entire cycle of the input signal, or we can say actually for the 360 degree of the input signal. Then that amplifier, it is classified as a Class A category. So basically, that if operating point is on the middle of the load line of the transistor device, then the signal will be flowing through the amplifier circuit throughout the input signals, or for the 360 degree. Then that amplifier, it is called as a Class A amplifier. Second category of the amplifier, that is the Class B amplifier. In Class B amplifier, the operating point, that is at the bottom of the load line, and there the conduction will be taking place just for the 180 degree of the input signal. That amplifier, it is classified as the Class B amplifier. In case of the Class B amplifier, the operating point, it is neither at the middle nor at the bottom of the load line. It is slightly above the load line. So the conduction in the amplifier circuit would be taking place for slightly more than 180 degree, but for less than 360 degree. That amplifier, it is classified as the Class AB amplifier. The fourth type of amplifier, that is called as a Class C amplifier. In case of the Class C amplifier, the operating point, it is such that the conduction, it doesn't take place even for the 180 degree. It takes place for a time period which is less than 180 degree. So that amplifier, it is classified as the Class C amplifier. So basically, that means for how much time period of the input signal the conduction takes place, on the basis of that amplifier could be classified as Class A, Class B, Class AB, and Class C. In case of, if we repeat it actually, in case of the Class C, Class A amplifier, the conduction takes place for entire input signal. For Class B, the conduction takes place for just 180 degree, and for Class AB, the conduction takes place for slightly more than 180 degree but less than 360 degree, and for Class C, the conduction takes place for less than 180 degree. So this is how actually the amplifier could be classified on the basis of the operating point. Now there is another classification of the amplifier. The amplifier could be classified even on the basis of the quantity which we are interested in the amplifying. Suppose that if you want to amplify the voltage of the input signal, and if output is also voltage, then that amplifier could be classified as the voltage amplifier. So in voltage amplifier, the input quantity which we are amplifying, that is voltage. The output quantity which we are getting, the amplified quantity which we are getting, that is voltage. So then that amplifier is classified as the voltage amplifier. Now the second category, that is the current amplifier. So as the name says actually, in current amplifier the quantity which we are amplifying, that is current, and the amplified quantity, the output, that is also current. So then that amplifier, it is called as a current amplifier. The third category, it is the transconductance amplifier. In transconductance amplifier, the quantity which we are amplifying, that is the voltage. So basically the input parameter, that is the voltage, and the amplified quantity which we are getting, that is the output current. So basically output current, it is a function of the input voltage. So then this amplifier, it is called as a transconductance amplifier. Now the fourth category, that is the transresistance amplifier. In transresistance amplifier, the input quantity which we are amplifying, that is the current, and the output quantity which we are getting, that is the voltage. So basically the output voltage, it is a function of the input current. So then that amplifier, it is called as a transresistance amplifier. Now that we'll look at that what are the different parameters with which amplifier could be characterized. See that if you take any object in the world actually, then that could be characterized with certain specifications. For example, that if it takes a vehicle actually, okay, so then vehicle could be characterized with the maximum speed which it provides, the average which it provides, okay, maybe the look actually, it's a carrying capacity, like that actually. Similarly, that amplifier, that could be characterized with that many specifications. For example, the first specification of the amplifier, that could be the gain actually. Gain is nothing but the ratio of that amplitude of the output quantity to the amplitude of the input quantity. Here in this presentation, the gain is written as magnitude of the V out by V in. It is written for the voltage amplifier. But say if it is say current amplifier, then the output quantity will be current, input quantity will be current. Then in that case, the gain is the magnitude of the output current to the magnitude of the input current. So one parameter with which amplifier could be characterized, that is the gain. The second parameter, that is the bandwidth. Bandwidth is nothing but the that frequency range over which amplifier could be used. We have seen in the beginning that amplifier could be characterized as the audio amplifier. Audio amplifier, they are capable to amplify the input signals whose frequency is within a range 20 Hz to 20 kHz. So that is nothing but the bandwidth of the amplifier. So second parameter, we can say that is the bandwidth of the amplifier. Now the third parameter, that is the efficiency. You see that amplifier, it basically amplifies the strength of the input signal. Now that in the process of amplifying the strength of the input signal, it takes energy from the supply voltage. Okay, now in this means it takes energy from the supply voltage, and that is how actually it amplifies the strength of the input signal. But in this process, certain power gets dissipated in the form of the heat. Okay, so means if the amplifier dissipates lesser heat, then its efficiency is better actually. It means that it is good in terms of converting the supply energy to the energy of the input signal. Okay, so efficiency is one of the that major parameters that with which amplifier could be characterized. Higher the efficiency, then lesser power will be wasted. Okay, and more the power which is obtained from the power supply, it is used in the amplification of the input signal. So efficiency, that is another parameter of the amplifier with which it could be characterized. The fourth parameter, that is the linearity parameter. See that amplifier actually, it has to amplify the input signal, but while amplifying the input signal, it has to maintain the shape of the input signal. If it is not maintaining the shape of the input signal, then amplifier, it is of no use. Okay, the reason is that means we cannot extract the information from the amplified signal. So basically that the shape of the output signal and shape of the input signal, it should be exactly same. Okay, the only difference should be in the in the form of the amplitude. Otherwise, the shape of the signal should be same. So linearity, it basically indicates that how good input signals and output signals are matching in the form of the shape. So that is again actually very important parameter of the amplifier. amplifier must have a good linearity, then and then it is useful, otherwise it is of no use. Now the fifth parameter, that is the noise parameter. Now when amplifier amplifies the signal, then maybe because of that the components, or maybe because of the environment, certain noise gets mixed with the input signal, and that is available at the output along with the that desired output signal. So if lesser noise is there, then we can say actually that amplifier is doing a good job. Okay, so noise is another parameter with which amplifier could be characterized. So lesser noise, it means if there is a lesser noise in the output signal, then that amplifier is good. Now the sixth parameter, that is the output voltage range. See again actually that let us take example of a real life object, say vehicle actually. Now if you look at the vehicle, that means if you look at the speedometer of the vehicle, then there will be maximum speed, okay, with which vehicle can provide. Similarly here also in the amplifier, that there could be the maximum voltage actually, maximum voltage level or maximum current level which it can provide, as well as there is that minimum voltage level or minimum current level which it can provide. So the output voltage range or output current range, that is again actually that one of the parameters of the amplifier. The next parameter, that is the slew rate actually, that is the that maximum rate of change of output voltage with respect to time. So basically that how fast that output changes with respect to time, that is that another parameter of the amplifier. It is called as a slew rate. The next parameter, that is the step response. Step response actually that it is that many parameters. Here 4 parameters are labeled, written in the slide. That those four parameters are rise time, fall time, settling time, then amount of overshoot. We'll look at the step response and we'll understand the meaning of these 4 parameters. Maybe that rise time and the fall time, they could be very easily understood. Suppose that our target is say 1 volt actually, and let us assume that the amplifier output is say 0 volt actually. So within how much time it reaches to 1 volt? Okay, so that is actually that characterized, that could be represented with the rise time. Generally that rise time actually, it is the time required for a signal to rise from 10% of the final value to the 90% of the final value. Now if we relate this it with the vehicle actually, so that the pickup of a vehicle, that could be related with the rise time. The fall time, that is actually that how fast the signal drops. Again actually that fall time, it is measured from the 90% of the final output signal to the 10% of the final output signal. And fall time could be related with the braking system of a vehicle. So if there is a better fall time, it means we can say that there is if the vehicle is having a better braking system actually, then it's similar to that amplifier having a that good fall time, better fall time. The another parameter which is connected with the step response, that is the settling time. So if our target, let us assume that if our target is 1 volt actually, so that if we apply the input signal, then within how much time actually that output reaches to 1 voltage. Okay, that maybe it will reach to 1 volt actually, but it will require certain time period to settle down at 1 volt. So that is what called as the settling time. Now this during settling process, that there could be some undershoot and overshoot actually. So that amount of the overshoot or amount of the undershoot, that is another actually that the parameter of the amplifier with which it could be characterized. Stability, that is again actually very important parameter of the amplifier. That if amplifier if it keeps on oscillating actually, then it is said that the amplifier is not stable actually. So and generally that the stability of the amplifier, it is measured in the form of the phase margin. Maybe that you will understand more about the phase margin in say higher semesters. But amplifier, it should be stable actually. Stable means that at the output there should be lesser number of the oscillations. There should be lesser number of ringing. then we can say that the amplifier is good from the stability point of view. So these are the 9, we have just discussed 9 parameters of the amplifier, but if you look at the data set of any amplifier, then you may find more parameters. But these 9 parameters which we have discussed, they are more than enough to understand about the amplifier. Now here I have taken one sample response of a sample frequency response of an amplifier. On y-axis, that gain is plotted. On the x-axis, the frequency is plotted, and the gain is plotted in the form of the dB. That is the decibel actually. For any value, you can find out the decibel. Suppose it's a voltage gain actually. You can find out the corresponding decibel value by following an equation that is a 20 log gain. So for example, let us assume that the gain of the amplifier is say 100 actually. Okay, and then if you convert this into decibel, then 20 log 100, you will get that is 40 actually. Okay, so that is maybe that more about this decibel and all those that you may study in some other subject. So the advantage of that converting the normal value to the decibel value is that we can cover the wide range. For example, let us assume that the minimum gain of the amplifier is 10 and the maximum gain of the amplifier is 10 raised to 5. So if you take the ratio of 10 raised to 5 to 10, you will get 10 raised to 4. This is a very wide range. But if you convert these values into decibel, now the 10, if you convert into decibel, 20 log 10, you will get 0 dB actually. And if you convert 10 raised to 5 into decibel, so 20 log 10 raised to 5, you will get 100. So basically that means initially the range was say 10 to 10 raised to 5, but now actually that range it is shrunk to just 10 to 100, and it could be easily plotted. So here the gain of the amplifier, it is plotted in terms of dB, and on the x-axis there is a frequency. Okay, so you can see actually that as the frequency increases, the gain increases. Okay, and at the maximum gain, that is equal to 10 dB. Okay, and at FL the gain is down by 3 dB. So this FL frequency, it is also called as a 3 dB frequency. And after FL means if you look at this corner actually, at this particular corner the gain is equal to 10 dB, and after that for very large range of the frequency the gain remains constant, and again at higher frequency gain drops actually. There are certain reasons that because of that gain drop we are finding lesser gain at the lower frequency as well as the lesser gain at the higher frequency. That you will study maybe that when you will go into the depth of the amplifier circuit. Now this FL actually, it is called as a 3 dB frequency. Even the FH actually, that is also called as a 3 dB frequency. The reason is that at FL and FH the gain is down by 3 dB. If you find out the normal value, then you will come to know that at FL the gain is equal to 0.707 of the maximum value. Okay, and if you convert this, if you find out the corresponding power, then you will come to know that at FL the power is that 1/2 of the power in the middle frequency range. So that's why that even that FL and FH, they are also called as the half power frequencies. So in this frequency response, it is the frequency response of some amplifier circuit. So if you look at this frequency response, so initially the gain is lesser. At FL the gain is 3 dB down. In the middle frequency range gain is constant, and at FH again the gain is that 3 dB down. So the useful frequency range, that is from FH to FL. So the amplifier whose frequency response is plotted over here, that amplifier could be used for amplifying the input signals whose frequency is within the range FH to FL. So basically that this slide it represents the frequency response of some amplifier circuit. Okay, and it also it also indicates the 3 dB frequency, that is 2 3 dB frequencies FH and FL. Okay, it also indicates that the bandwidth of the amplifier is from FH to FL. So that is about the frequency response, some information about the frequency response of amplifier. Now when we were going through the specifications of amplifier, that one of the specifications that is the step response. So here that step response, it is explained with the drawing. Here it is assumed that the input signal, it's a step signal, okay, and the output signal, you can see actually that it is not exactly same as the step signal, but it requires certain time actually to rise. Okay, so from the output actually, that from the 10% of the V2 minus V1 and from 90% of V2 minus V1, we can actually measure the rise time. Okay, and you can also see that output actually, it doesn't settle to the final value immediately. It requires a certain time period for settling down. So that time actually, it is called as the settling time. Okay, and you can also see that there is overshoot in the output jumps, as well as that there is some valley in the output actually, or it is said as overshoot and undershoot. So we have seen in the specifications of amplifier that this overshoot and undershoot, they are also the parameters of the amplifier with which amplifier could be characterized. So if lesser overshoot is there, or if there is lesser undershoot, then that amplifier generally it is said that it is good in the response. So if settling time is lesser, if rise time is lesser, if overshoot is lesser, if undershoot is lesser, then that amplifier, it is characterized as a comparatively good amplifier. Okay, so now if we summarize actually till now what we have studied, we studied about that analog circuit, we studied about the digital circuit, we studied about analog signal, we studied about digital signal, we studied the function of amplifier, classifications of amplifier, we studied specifications of amplifier. So basically we have got overview of the amplifier. Now that we'll look at the one kind of special amplifier, which is called as an operational amplifier. Now operational amplifier, it was used in the analog computers to perform various mathematical operations. That's why actually that it is called as an operational amplifier. You can carry out any mathematical operation using the operational amplifier. Mathematical operations such as summation, even taking the difference of two signals, or say integration, differentiation. You speak out that any mathematical operation that is possible to be carried out with the operational amplifier, and that's why it is given the name operational amplifier. Now in earlier days, this operational amplifier, it was constructed using various discrete components, but nowadays with that advancement of the technology, these operational amplifiers, they are fabricated in the form of the integrated circuits. So then we will get a better performance from the operational amplifier. Now this is the symbol of the operational amplifier. It's represented with that triangle. Okay, generally that op-amp actually, in the coming slides we'll see about that one op-amp, that is a very popular op-amp 741. It has 8 pins actually. Okay, now here in this symbol 5 pins are shown. One pin, it is indicated with the plus sign. Okay, that it is called as a non-inverting pin. The other pin, it is indicated with the minus sign. It is called as an inverting pin. There are 2 supply pins, Vs plus where a positive supply is applied, and Vs minus where negative supply is applied. Okay, and then there is one pin actually. It is the output pin. So here 5 pins are shown: non-inverting pin, inverting pin, the pin where positive supply voltage is applied, and the pin where negative supply voltage is applied, and the one pin that is the output pin. Now op-amp actually, it's basically amplifier. Okay, and there are certain that properties we expect from an op-amp. So those properties are called as the ideal properties of the operational amplifier. Now operational amplifier, that it's basically that amplifier. Okay, so that whatever the specifications of the amplifier, all those specifications will be there in case of the op-amp. So first of all, actually that open loop gain actually. Okay, so we expect that the op-amp, it should provide infinite open loop gain. Its gain should be as high as possible. Okay, so that is one parameter actually we expect from the op-amp. Its gain, open loop gain, should be infinite. The second the parameter, that is the input impedance. Okay, we expect that op-amp should provide infinite input impedance. Okay, that let us say that why actually that we are interested in infinite input impedance. If input impedance of the op-amp is high, then the loading on the previous stage will be lesser. That is the reason that we want that we are interested in infinite input impedance, because that then the op-amp will be less loading the previous stage. The third parameter which we expect from operational amplifier, that is the bandwidth. We expect that op-amp should provide infinite bandwidth. So then it could be used for amplifying signal with any frequency. We have seen frequency response where the bandwidth was FL to FH. So in case of that operational amplifier, we want that FL should be close to 0 and FH should be close to infinite. Then its bandwidth will be infinite. Now the fourth parameter which we expect from operational amplifier, that is its output impedance should be as low as possible. Okay, so that output impedance, that ideally speaking, that it should be 0. Why? What is the reason that we expect 0 output impedance? The reason is that then it can drive the load in a better way. So that is the reason actually that we expect that operational amplifier should provide 0 output impedance. Now the fifth parameter which we expect from operational amplifier, that is that its input offset voltage, that should be 0. Now maybe we'll go back to the symbol to understand what is the meaning of the input offset voltage. Now if you see that basically operational amplifier, what it does actually, it takes the difference of the input signal and then that is what actually it amplifies. Okay, so means if the difference is equal to 0, if the difference between say V plus and V minus, if that is equal to 0, then output should be equal to 0. Okay, but because of that some mismatch in that input components, that it may happen that even when actually that that to get the output equal to 0, you need to apply certain the difference between the V plus and V minus, then the output will be equal to 0. So that difference which required to be applied to get the output voltage equal to 0, that is what called as the input offset voltage. Generally that this input offset voltage, it's not actually that desirable property of the amplifier. It should be as minimum as possible, or ideally speaking it should be 0. But because of that mismatch in the input components which takes place take place during the fabrication, that input offset voltage will not be equal to 0, but it will be it could be slightly more than 0, maybe say 1 millivolt, 2 millivolt. It depends upon that how accurately op-amp is fabricated. So basically that input offset voltage, it is nothing but the voltage which is required to be applied at the input of the op-amp such that the output becomes 0. Ideally speaking it should be 0, but because of that mismatch in the components, it may not be 0. Okay, the last the sixth parameter, that is the slew rate actually. Slew rate, it indicates the speed of the op-amp, that how fast that output can change. Okay, so ideally speaking that we expect from the op-amp that the its slew rate should be infinite. So slew rate, it is generally denoted with the dV out by dt, and it should be infinite. It should be as large as possible. Okay, now that two more parameters we will be discussing. One is that common mode rejection ratio. I'll explain you that what is the meaning of common mode rejection ratio. But from op-amp we expect that common mode rejection ratio should be infinite. Okay, now let us understand what is the meaning of the common mode rejection ratio and what it indicates. See, basically that we are interested in amplifying the difference of the input signal using op-amp. But because of that the circuit configuration, that it may even amplify the average of the input signal along with the difference signal. Okay, so means if the ratio of the so basically that first you measure that how good it is amplifying the difference of the input signal. Okay, and note down the gain. So let us assume that the gain for the difference of the input signal is say AD. Okay, then you find out actually that whether it is amplifying any common part of the input signal or not. Okay, so let us assume that for the common part of the input signal, the gain is equal to say ACM. Okay, so for ideally actually we want that ACM should be close to 0 and AD should be close to infinite. Okay, so the ratio of the AD and ACM that is indicated with the parameter which is the common mode rejection ratio. So for example, let us assume that AD is equal to say 10 raised to 5 actually. Okay, and ACM that is equal to say 1 actually. Okay, so then ratio of the AD to ACM that is 10 raised to 5. Now you convert this into dB, so you'll get that is a 20 log AD by ACM, you will get 100. It means actually CMRR that is equal to 100. For that we expect from the op-amp that AD should be as large as possible and ACM should be as small as possible. Okay, because that the major application of the operational amplifier that is to amplify the difference of the input signal. So this CMRR, it is again actually very important parameter of the op-amp. Now the last parameter which we will be studying, that is the power supply rejection ratio. Now let us understand actually that what is the meaning of the power supply rejection ratio. Again actually this should be we expect it from the op-amp that this parameter should be infinite. Now we have studied about the input offset voltage. Okay, that input offset voltage, it should be close to 0, but because of the mismatch in the input components, it may not be 0 actually. It could be some value, maybe 1 millivolt, 2 millivolt, 3 millivolt, some value could be there. Okay, now so input offset voltage, it is undesirable. It's not a parameter of interest to us. Okay, but suppose that that parameter it is present, it is having a non-zero value, then its value should remain constant. It's not vary with the variation in the supply voltage. So basically that power supply rejection ratio, it indicates that whether that this input offset voltage, it is a function of the supply voltage or not. Okay, ideally speaking, it should not be the function of the supply voltage. Okay, so PSRR it just indicates that whether the input offset voltage, it is a function of the supply voltage or not. Okay, and in PSRR there could be positive PSRR and there could be negative PSRR. So in case of the positive PSRR, the supply voltage, it is increased in the positive direction, and input offset voltage is measured. That means in what direction or by what amount the input offset voltage is changing. So that is what called as a positive PSRR. Okay, in case of the negative PSRR, the supply voltage, it is changed in the negative direction, and then input offset voltage is measured, and it is observed that whether the input offset voltage is changing or not. So that is what called as the negative PSRR. So basically in today's talk actually, if we summarize the topics which we have studied, we studied about the amplifier, what is the function of the amplifier. Okay, we have seen that it is opposite to attenuator. Then we have seen that amplifier classifications. Okay, then we have seen little bit about that analog circuits, digital circuits. We have studied about we have studied about various specifications of the amplifier. Then we looked at the op-amp introduction. We have looked at the properties of that ideal op-amp. So basically that these are the topics which we have covered in today's talk. Thanks a lot.